Amit. Okay, so our first speaker in this session is Amit Shah from the University of Leeds, and he will tell us about exangulated functors.
Okay, thank you very much, Johanna. And yeah, thank you to the organisers, Karen, Siva, and Johanna, for giving me an opportunity to speak. Is the sound okay? Everyone can see the screen? Okay, perfect. This is the first time I'm using this to properly share, so we'll see how it goes. So yeah, I wanted to speak about these higher functors between exangulated categories. And of course, you can talk about this in the classical dimension of n=1 as well. I'll start off by giving some motivating examples and talking about some work in progress with Raphael Bennett-Tennenhaus, Johanna Haugland, and Sandøy. I hope I pronounced that well, but maybe Johanna can tell me later. Yeah. Okay. So what do I want to talk about? The main motivation is to understand functors going from some category A, which has some structure. Maybe it's n-exact, maybe it's n+2 angulated, maybe it's just triangulated, going across to some other category B, where the structure here might not be of the same length. So it might be exact, or it might be n-exangulated or something like this. So I'm kind of mixing the dimensions of the structures. And this is what I mean by an n structure or an m structure. Okay, these n's and m's are just positive integers, possibly different. And structure compatible just means that we're taking some n+2 angle, some n-exact sequence, and sending it across to some number of m sequences, whatever they are, mx angles or whatever, and such that it splits up in a nice way. Okay, so I don't really break the structure in some sense. The m structure can detect the n structure. So let me give some examples. So some classical examples are when you go from an exact category to an exact category. Okay, so A and B have the same structure. And then the functors that we like to think about are ones that Sondra talked about earlier on, which is where short exact sequences should go to short exact sequences. And in the triangulated case, of course, there's the analogy is these triangle functors or triangulated functors. So thankfully in the literature, these are all well studied, and we've got plenty of examples of these things. And they're very useful, and they show up in representation theory all over the place. So this is why they've generated a huge amount of interest. And so you might go, well, all you're doing is putting the name of the category in front of the name functor. And so this is where kind of it's more interesting when we mix up the structures a little bit. So we might start asking about how I can go from an exact category to a triangulated category in a structure preserving way. So what does that mean? So that means that short exact sequences should go to triangles. And some examples then are where you think about a module category being included into its derived category as the heart of the canonical T structure. So in that case, then the short exact sequences should go to triangles and kind of not mess around with the structure at all there. But then we don't have any terminology to talk about these things, yet there are plenty of examples. And this is where the theory of X-triangulated categories, as defined by Nakok and Palu, come into play. So these categories are a generalization of exact and triangulated categories, a simultaneous generalization. And just as a quick reminder as to what they are, so they're quite new, so maybe not a reminder, but they consist of an additive category A, a biadditive functor boldface E that I have here, going from A op cross A to the category of abelian groups. And then this frac S, this is just an additive, or what's called an additive realization. So what it does is it assigns to each element delta of my my extension group, this boldface E, C, A. It assigns an isomorphism class of a complex of the form A to blah to C. Okay, and the isomorphism is given by fixing A and C, and then the middle, the map between the middle terms is asked to be an isomorphism. Okay, so some examples of this include triangulated categories, as I said, and what's the structure. So in this case, that the biadditive functor bold E is given by homing into the shift of an object. So you can really think about this boldface E as some map here, delta going from C to the shift of A, and then this whole thing then is called an X triangle, where I've really associated to this delta, this sequence ABC, this one here. And we just call this an X triangle. Of course, there are analogous notions for the exact case as well. So in the exact case, you would just get your first extension group as your boldface E there. And what I talk about will focus on the angulated stuff, but there are analogous notions for the exact setting as well throughout all of this. So with that notation, with those categories in mind, Raphael and I defined these X triangulated functors, going from now one X triangulated category A to another B. And all we ask is that it sends X triangles on the A side to X triangles on the B side. So E X triangles to F X triangles. And they're just the notion that you would want. They just preserve the structure of the X triangulated category. So let me just touch on the definition of that a little bit as well. So the way we define it is by asking for the existence of this natural transformation gamma, which kind of tells you how you should go from E extensions to F extensions. And so there's more involved. It has some compatibility conditions with F, with the functor F. But it looks very similar to what we'd ask for in a triangulated functor. One key difference is that we only ask for this to be a natural transformation, not a natural isomorphism. But it just so happens when both of your categories are triangulated, you actually get a natural isomorphism and a triangle functor back. And again, analogous things with exact functors. And so with this now, we can talk about functors from exact categories to triangulated categories, which preserve the structure. Then these are the X triangulated functors. So let's skip up a dimension. So now we have the higher homological algebra setting, and we've got n-exangulated categories as defined by Herschend, Liu, and Nakaoka. And examples of these then are the Geist-Keller-Oppermann n+2 angulated categories. So Raphael also, we defined the n-exangulated functors, just these higher notions of X triangulated functors. So they just go from an n-exangulated category to an n-exangulated category and preserve the structure. Okay, so this is all kind of what we've done so far. This is all known to us. And now with Johanna and Mats, we started to look at kind of mixing up the structure a little bit more. So now we might go from an n-dimensional structure, okay, so an n+2 angulated category, for example, and then down into a triangulated category. So some more refined structure. So this triangulated category is picking up some more information. And of course, the motivating examples come from when you have an n cluster tilting subcategory closed under the nth shift, sitting inside a triangulated category. So then Geist, Keller, and Oppermann tell us that T, this n cluster tilting subcategory, is n+2 angulated. And the structure, this n structure on T, is given by these towers of triangles. So here, every oriented triangle is a triangle in my triangulated category. And the connecting morphism from T0 to the nth shift of Tn+1 really is this composition going all the way from the right to the left there along the bottom row. Okay, so what's this telling us then? Well, it's telling us that we can go from one n+2 angle, so this whole thing along the top, and we can pick out n 1+2 angles, or n triangles, sorry. And so, of course, then we can think of functors between, or going from an n-exangulated category to a 1 category of some sort. It should take one n-x angle and give me back n 1x angles. So to talk about these functors, or to define these functors in the way that we came up with, we need this notion of a category of E extensions. So given an n-exangulated category, we can talk about or look at the category of all E extensions. So the objects are just any element delta of ECA, where C and A can vary as much as they like. So that's the category we use. And then what we call an n1 exangulated functor is a functor going from an n-exangulated category to an x-triangulated category. So an example might be from an n+2 angulated category to a triangulated category, as we've just seen. And what it should do is it should take one kind of long extension, one delta, and then give me back n different 1x angles on the right-hand side. And then there's some nice kind of compatibility conditions that we need to ensure that this functor E behaves nicely with the assignment of objects. So that's kind of, I think we're kind of happy with this so far. And the next thing now is we're just going to start looking at when 1 gets bigger as a nice generalization. But this somehow seems to be more complicated than we've found to find examples so far. So that's all I wanted to say. Thank you.